Hello, my name is Nitesh and I am going to talk about the topic that is, so we are going to discuss the word electrostatics first, right? So what is the meaning of word electrostatics? Let us first understand the term electrostatics. So electrostatics is composed of two words. That is, if you divide this, so one is electro. This electro means electron. It is a charge. Okay. Now the second term that is over here is statics. Statics means at rest. So we can say when we talk about the electrostatics, we talk about the term the charge is at rest, right? So we'll say the charge is at rest means in this chapter we are going to talk about the term charges at rest, right? Now moving on, where does this word electron comes from? So in Unani language, in Unani language, there is a word. The word is amber. So this amber, if you convert this word in English, so it is termed as electron, right? Moving ahead, we are going to talk about the charges, right? Because this chapter specifically talks about charges, so we are going to talk about the charges a little bit more. So let's start with the charges. So what are charges? Let us first understand the term. What is the meaning of charges? So the charges are the charge is what is the charge? Charge is the intrinsic property. Charge is the intrinsic property of fundamental particle of matter. So there are students. There are two kinds of fundamental property of matter. There are two kinds of properties. One is intrinsic and other is extrinsic. So the charge is intrinsic property. What is intrinsic property? So intrinsic property, we can also call this is a very fundamental kind of property, right? Now if we on the basis of their polarity, we know there are two kinds of charges, positive and negative charges. Okay. Now you have also heard about the experiments in which there are positive charges and there are negative charges on different kinds of, because earlier we were not knowing that what are the kinds of charges that were available to us, so we used uh, certain kind of experiments to identify the type of charges. So let us give you a few examples for the positive charges and negative charges. So for positive charges, let me say that let you make a table. Let me make a table. That is, suppose glass rod, it is positively charged. Cat skin, it is positively charged. Now, moving ahead, we can also name certain other examples. That is, woolen cloth. This is also positively charged. This is also, let us say, woolen carpet. Now, silk. Silk is negatively charged. Why am I mentioning all these kinds of substances over here? Glass rod, cat skin. What is the use of all this? So the use of all this is, if we rub glass rod with silk, the glass rod, in glass rod there comes positive charge, and in silk there comes negative charge. In certain exams or in the many kinds of lectures also, we come to know about the type of charges in glass rod, what kind of charges appear if we rub the glass rod with silk, if we rub cat skin with fur, so what kind of charges come. So this is all about that we should know what kind of charges comes on different, like glass rod, cat skin, woolen cloth on carpet. Okay. So what kind of charges come on negative? So let me say that ebonite rod, if we use ebonite rod to rub with cat skin, in this ebonite rod, there will be negative charge, and cat skin there will be positive charge. Okay. Or there is other kinds of things, that is, one is amber, rubber. So in all these, there comes negative charge. How does these charges come? So the method of acquiring these charges is known as frictional electrification. Frictional electrification. And what is frictional electrification is? So frictional electrification means when you rub two bodies, because bodies are generally in neutral, but if you rub these two bodies, so in certain cases, one of the body may acquire positive charge and other of the body may acquire negative charge. So that is how we come to know about the types of charges on the basis of their polarity. I hope you understood. Now moving on. So let us talk about the modern theory of electrification. Okay. So what is the modern theory of electrification tells? The modern theory of electrification. What does it tells us? So it tells us the modern theory of electrification that there are two kinds of charges, that is positive and negative, which in general negative is termed as electron and the positive is termed as proton. Okay. So what we should remember about them, that proton is positive, electron negative charge, and the charges on both of them, if you talk about the magnitude of charge, that is similar. But here it is 9, sorry, it is 1.6, 1 plus 1.6 10 की power minus 19 coulomb. Here it is minus 1.6 10 की power minus 19 coulomb. The masses of both of them are also important because in certain cases they have been asked what is the mass of proton. So the mass of proton is 1.67 10 to the power minus 27. Mass for electron is 9.1 10 to the power minus 31. That is in kg. That is in kg. Right. Now, you should also remember that mass over electron is approximately, let us say approximately, it is approximately 1837 times mass over proton. This is also important when you solve numerical, these kinds of questions come, so you should remember this also. Now, what happens when we rub two bodies according to modern theory of electrification? Suppose we rub two bodies. So, if electron on rubbing, what happens? If electrons is lost, electron has certain mass. Okay, so body will acquire positive charge because electron is lost. It means the negative charge is deficient now. The body is deficient of negative charges. In that case, there will be excess of positive charge and body will be positively charged. If electron is gained, right, so there will be negative charge because on the body there will be excess of negative charge. What happens to mass? Can you guess what happens to mass? Okay, so look, now let me tell you what happens to mass. Actually, the mass is increased if the body gains electrons because electron has certain kind of mass. And if the body lost electrons, the mass gets decreased. This arrow downwards indicates decrease and the arrow upward indicates increase. Okay. In general, we use these arrows. Right. Moving ahead. There is a very important line that you have read. And if you haven't studied, so let me tell you. The line is repulsion is a sure test of electrification. Repulsion is a sure test of electrification. Right. So how do we come to know about electrification? So we use the repulsion test. It means if two bodies are repelling, in that case, there is a electrification. Okay. So this line is very important. If someone asks you what does this mean? So it means that the repulsion between test bodies. Okay. So there are two test body and a charged body. Let us consider. Let me explain you with this a certain example. Let me say this is a test body, right? We don't know what kind of charge is over it, and here it is a charged body, right? So we have two bodies, charged bodies and test bodies. If we rub the charged body and test body, so there is likely to happen repulsion if there is a similar kind of charges on both of them. If there is similar kind of charges, so there is going to be repulsion. So we come to know about that these two bodies are electrically charged. Understood? Now moving ahead. Let us talk about the properties of charge. Okay. So what are the properties of charge? Because we are talking about charge specifically because this whole chapter is based on charges. So let us first talk about the properties of charge. The first property is very important that like charges attract, right? No, it's wrong. Like charges repel. Okay, because I have earlier told you this. So like charges repel and unlike attract. Unlike attract. Now, the second part. The second part is it is very important to know that a charged body, and let me make this star over here, that is a charged body attracts light uncharged bodies. What I'm talking about this? Why I'm talking about this? A charged body attracts light uncharged body. Because once a student has asked about this, that sir, is it possible that a charged body can attract a neutral body? So it is possible because charged body can attract light uncharged body. Yeah, let us say that it is a kind of neutral body. And how does this come? So this happens due to electrostatic induction. Electrostatic induction. Okay. This induction term we are going to talk about later in the method of charging. So keep a hold over here. Now moving ahead. The third part. What is the third property? The third property is that charge is conserved. Okay. So what is this? The charge is always conserved because charge is conservation means it can neither be created nor be destroyed. Okay. So this is very important point. Now the fourth part is charge is quantized. Charge is quantized. Okay. So charge is quantized. It means that charge is always formed in the integral form, where n is an integer and E is the charge or electron, that is 1.6 10 to the power minus 19 coulomb. It means that we cannot obtain charges like 1 by 2e, 2 by 3e. This is not possible. However, let me also tell you, students, that it is not possible that we are going to get 0.75 electron. We are going to get 1 electron, 2 electron, because we are going to get in the form of integer. That is plus minus 1, plus minus 2. So these are all integers. Understood? Now, you might have heard a, a very familiar term, that is quark. What are quarks? So quarks are kind of fundamental subparticles of these electron proton. So let me call them as subparticles. And there are two kinds of quark. One is up quark and another one is down quark. So what is up quark? So up quark is plus 2 by 3e and down quark is minus 1 by 3e. However, this up quark and down quark does not nullify the quantization property of charge. It's very important to understand. Okay, understood? Now, so these are kind of charges. Also, the fifth property, that charge is invariant. Or what is the term invariant means? So we will explain it further. That charge is invariant. Invariant means it is not affected by motion. It is not affected by motion. Okay, understood? Fifth property is charges are additive in nature. Charges are additive in nature. Right? Now, moving ahead, we are also going to talk about the conservation and the quantization of charges in detail. Okay, so we'll talk about these two properties in little bit details. Okay, so let us first talk about the conservation of charge. Okay, let me mention the term conservation of charge. Right. So what is conservation of charge? Already told you that charge can neither be created, charge can neither be created nor be destroyed. Okay. So there are some examples of this conservation of charge. That is electrification by friction, electrification by friction, or let us say that charging by friction. Electrification simply means charging. Okay. And also electrostatic induction. electrostatic induction. Okay, so in all these methods, the body is the electrons in the body are, you know, they are transferred from one body to another, but net charge remains same. Okay, so what happens? The electron is transferred. Okay, the electron is transferred, but net charge, let me say that Q net is constant. And when the net charge is constant, the conservation of charge is there, right? Now, moving ahead, let us talk about few examples of conservation of charge. So the examples are, the first example is glass rod, glass rod rubbed with silk, rubbed with silk. Second example is, I think the pen is getting a little bit thicker. Okay, now the second example is, that is in nuclear reactions also. So let me also mention one of the nuclear reaction which is very famous. In nuclear reactions also the charge is conserved. The reaction is uranium 238. So it gets splits into thorium 9234 plus alpha particle, that is, this is alpha particle. Okay, 2He4 is alpha particle. So this is a nuclear reaction in which this also, in which it is also conserved. Okay, in which the charge is conserved, right? Also very famous example, that is pair production, in which the charge is also conserved. So what is pair production? It means in this case the gamma is divided into positron and electron. Okay, positron and electron. This is electron and this is positron. Right. Moving ahead. Let us also talk about the quantization of charge. Okay. So talk about the quantization of charge over here. Quantization of charge. Here we'll talk about the quantization of charge in little bit detail. Okay. So Q is equals to plus minus NE. What is N? N is an integer. Right. N is an integer. Okay. So what does this tells us about? It tells us about the charge is only formed in obtained in the form of integers. Already discussed, but I'm telling you again. The charge can only be obtained. Let us say, let us put n is equals to 1. So we can get q is equals to 1e. We can get q is equals to 2e, minus 2e, minus 1e. But we are not going to get as 0.75e because it's not possible, right? So this is one about the quantization of charge. Okay. Now, moving ahead, we'll talk about the very famous law, that is Coulomb's law. Okay, so let's start with the term Coulomb's law. Okay, so let me put a heading over here, that is Coulomb's law. Let me tell you what is Coulomb's law. So in the year 1785, the Coulombs tell us about a law that is known as Coulomb's law. What does this tells us? It tells us that force is directly proportional to Q1, Q2, that is magnitude of charges. Suppose there are two charges Q1 and Q2. They are situated at a distance r from each other. The force acting between them is directly proportional to product of their charges, and it is inversely proportional to its square of distances. Right. So if we uh, put them together, we will come to know that F is directly proportional to Q1 Q2 by r square, which we can replace directly proportional sign by putting a constant over it. That constant is k, and q1 q2 by r square. Okay. Now moving ahead, let me write it down as, what is k? So k is equals to 1 by 4 pi epsilon naught, that is equals to 9 into 10 to the power 9. This is the value of K. The unit will be Newton meter square coulomb to the power minus 2. This is the value of K. What is epsilon naught over here? So the epsilon naught is absolute permittivity, absolute, sorry, absolute permittivity of free space. The value of epsilon naught is 8.854 into 10 to the power minus 12, right? Also, let me tell you, you know that force is a vector quantity. So, if it is vector quantity, vector, I have written two times, sorry. It is a vector quantity. So, for a vector quantity, we are going to talk about the Coulomb's law in vector form also, right? So, let us talk about the Coulomb's law in vector form also. Okay, moving ahead. Oh, sorry, I have written Coulomb to the power minus 2, not it is not going to minus 2 because we have already put it in the denominator, so it will be Coulomb square, right? Moving ahead. Also, let me tell you this thing that we can also obtain the value of epsilon naught. Okay, uh, but we don't need this value. Generally, use this value 9 to the power 9. Okay, this is important. So while solving numerical, let me tell you, you can directly put this value and then solve that. Now, so in vector form, it is very important to understand Coulomb's law in vector form. And the thing is that most of the time we do not understand how to write the Coulomb's law in vector form. So let me explain this also. Coulomb's law in vector form. Okay, now suppose there is a charge Q1 over here. Okay, and there is another charge that is Q2 over here. Forces will be acting. So force will be acting on this charge Q2 due to Q1, and the force direction of the force will be in this direction. So we will say F21. How we remember this, that F21 means on 1 on 2 due to 1, right? Now the direction will be R21 cap. In this direction it will be F12 force, and the direction will be R1. Understood? Now let me write these two things, and so if we write the value of F12, so we can write the value of F12 as 1 by 4 pi epsilon naught Q1 Q2 by R cube and R to the power 1 2. Sorry, R1. And let me say this is question number 1. Moving ahead, F21 can be written as 1 by 4 pi epsilon naught Q1 Q2 by R cube R21. Equation number 2. Now let me also tell you how does this cube comes and why have we replaced this vector. So this R cap means it is a unit vector. So we can write this as R cap as R12 vector divided by magnitude of R12. So I have replaced this R12. There will be R12 cap, and when you use this, so this will come as R12 over here I'm talking about. So this will come as R12 and divide by this R mod of R. So it will become this R multiplies and it becomes R cube, and here it comes as this. I hope you understood this. Very important thing also. Now, now you understood this. Okay. Here, if you compare these two values, F12 and F21, these are almost equal. This term and this term is almost equal. Only difference is this R12 and R21. As you can see, R12 and R21 are acting on the opposite directions. So we can write this as F12 because vector is force is a vector quantity. We can write this F12 is equals to minus of F21. And this also tells us that Newton's law holds true for electrical forces. What I'm telling you, that Newton's law holds true for electrical forces. Right. Now, also we can write for the multiple charge, that is superposition principle. So for multiple charges, there comes a superposition principle, that is from Coulomb's law. This principle is known as superposition principle. Okay, what does this principle tells you? In simple terms, I'm going to tell you that how to remember this for multiple charges. That is, Fn is equals to F1 plus F2 plus this is F net. Okay, dot 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 plus यहाँ लगा दीजिएगा plus Fn, right? So this is in general sense this is superposition principle, and with diagram let me tell you. This is y, this is x, and here it comes as A and B. Okay, now let us say that at point A there is charge q1, at point 2 there is charge q2. Okay, and from the center the distances are r1 and r2. So in this direction there will be a force acting, as I have mentioned above, F12, and in this direction there will be a force acting, that is F21. Similarly, the distance between them is R21, right? And also let me tell you, let me mention that it is Q1 over here, it is Q2 over here, right? So we can write this as, let me write F12 is equals to 1 by 4 pi epsilon naught Q1 Q2 divided by R1 minus R2 to the whole cube R1 minus R2. This is in vector form. Okay. Now, moving ahead. Now, we will talk about the SI units for this charge, obviously, and very important, as you know, we have mentioned earlier also. Let us talk about the SI unit of charges. SI unit of charge, right? So there are the SI unit of charge. One is Coulomb. Okay, so Coulomb is very famous, but many of the times there is a question that is being asked, and that is a very important question. That in 1 Coulomb, how many number of electrons gets transferred? Something like this. The question is, in 1 Coulomb, electrons gets transferred from the charge. The value of charge is 1 Coulomb. So for 1 Coulomb, let me rephrase this. As for 1 Coulomb, the number of electrons that is get transferred, electrons get transferred from one body to another. So you have to find the value of n, that is number of electron. Okay, the question is like this, something like this. I haven't phrased the exact the language of the question, but somewhat the question is like this. And I think you should use this and equation, that is q is equals to ne, and you can get this value, that is 1 Coulomb divided by 1.6 to the power minus 19, and the answer that comes is 6.25 10 to the power 18. This is important. So if we are asked to define 1 Coulomb, so you can say when the 6.25 to the power 18 number of electrons get transferred from one body to other, this number of electrons get transferred from one body to other, the charge is 1 Coulomb. Okay, so I have this rephrase in the form of question. I hope you understood. There are certain other units of Coulomb charge, that is, let me say that you can also say that 1 Coulomb is equal to 3 into the power minus 9 static Coulomb. Stat Coulomb लिखते हैं इसको. Okay, this is equal to a static unit, and also you can say that 1 EMU. This electromagnetic unit, this electrostatic unit, and this electromagnetic unit, that is equals to 10 coulomb, and that is equals to 3 into 10 to the power 10 stat coulomb. Okay. So this is important. Also, one electron, the charge of electron you already know that is 1.6 to the power minus 19. This is important. This is needed. However, these are not generally asked, so if you don't memorize them, it's all right. But if you need to memorize this only, okay, and this also. Now, let us talk about the validity of Coulomb's law. This is very important. Conditions of validity for Coulomb's law. Let me write this: condition of validity of Coulomb's law. Right. So the two important things are there. First is that the distance for the verification of Coulomb law distance will be 10 to the power minus 15 to 10 to the power 18 meter. It means that the distance for the between the charges, okay, the distance between the charges, I'm talking about R, this R, Q1 and Q2, this R should not be less than this 10 to the power minus 15. Why? Because this 10 to the power minus 15 means 1 Fermi, right? So 1 Fermi is actually the nuclear distance. I have to write this whole Fermi over here, okay? So 1 Fermi is actually, what is this? This is a nuclear radius unit. So if you go below this 1 Fermi, you will go into the nuclear forces. And nuclear forces are very strong forces, and in that case, the Coulombian forces will not act there. So it should not be less than 10 to the power minus 15. Not should be greater than 10 to the power 18 meter, right? So the distance should be in between this. Moving ahead, and the second point is that the charge should be a point charge. The charge should be point charge. Coulomb law is only valid for point charges. What is a point charge? So let me tell you what is a point charge. A charge whose size should be less than the separation between them. Separation between them. Right? So that is a point charge. Okay.